Alright, welcome to the last section of our course. So we're in section 8.6, talking about constrained optimization. So for this section, we're going to be looking at the concept of maximizing and minimizing a function of several variables subject to a constraint, so some sort of restriction on those functions. When we're looking at practical application, the most common constraint that we deal with is a budget constraint. Okay, so this company is going to produce so much of each material, and how can they maximize their profits? Well, if they could keep producing items forever, then they would just make more and more and more and make more money. But of course, there is not an infinite amount of money to be spent, so oftentimes we need to figure out how can I maximize profit or minimize cost or whatever the case may be, given that restriction, okay, that constraint. So we're going to look at this as a concept first in our first example, then we're going to look at our method for solving exactly. We're going to try an example, and then look at some more interpretation. So let's start off here. A company has production function f of xy equals x to the 2/3 power times y to the 1/3 power, and budget constraint 100x plus 100y equals 378,000. So for part A, if $100,000 is spent on x, how much can be spent on y, and what is the production? So first up, for part A, so our budget constraint right here tells us I have 100x plus 100y equals 378,000. So that tells me it's costing, or the amount of money that I'm netting out of this is going to be, no, I was right, that's on the cost, sorry about that. So the cost of making a unit of x is 100, cost of making a unit of y is 100, and they have $378,000 total to spend. So, if they spend $100,000 on x, how much can be spent on y, and what is their production? So, spending $100,000 on x means the company has $278,000 left to spend on y, right? Because if they have $378,000 total, then of course that means that they would spend $100,000 on x, and then the remaining $278,000 would be left to spend on y. So we have the total cost of x, so 100x would be equal to 100,000, and 100y would be equal to 278,000. So we get $100 per item for x, spending $100,000. Solve for x, that would give you x is 1,000, and then 100y equals 278,000, gives us 2780 for y. Thus, x equals 1,000, and y equals 2,780. Okay, so thus, if we are looking at the production level when we spend $100,000 on x and $278,000 on y, okay, we're producing 1,000 items of x, and we're producing 2,780 items of y, whatever those are. So if we're looking at the function, so f of 1,000, 2780 equals, so let's look back at the function again, right? It's x to the 2/3 times y to the 1/3. So that's going to be 1,000 to the 2/3, and I'll put that in just a second. times 2780 to the 1/3. So let me just put those in real quick. So that's 1000x, so that's x to the 2/3. And the y value gets raised to the 1/3 power. Okay. And if we go ahead and kind of plug and chug those numbers, we get about 1,406 units produced. Okay, so that is the production of this product, whatever it is. Okay, so just imagine like if I was running a lemonade stand, right? And I'm going to need lemons and I'm going to need sugar, right? So what this is saying is, in this ludicrous example where I spend, I have a budget of $378,000 for my lemonade stand. So let's say $378 for my lemonade stand, right? If I spend $100 on lemons and $278 on sugar, how much lemonade can I produce? And that, in this case, would be 1,406, right, glasses of lemonade in this hypothetical situation. Okay. So then, for part B, it's saying if $200,000 is spent on X, how much can be spent on Y, and what is the production? So we're going to have a similar argument here. So spending $200,000 on X means the company has how much left? Just $178,000 left to spend on Y. So if we set up our cost equations here, that's 100x equals 200,000 this time, and 100y equals 178,000. Thus, if we solve for x and for y, so divide 200,000 by 100, x is 2,000, and y is 1,780. Okay, so those are the quantities of those products, right, that we're going to put in to make our whatever our item is, right, our production. Thus, if we're looking at the function now, f of 2,000, 1780 equals, so x to the 2/3 times y to the 1/3. So x is 2,000 to the 2/3 times y, which is 1780, to the 1/3. So I'll just put those right here. So there we have our x to the 2/3, y to the 1/3. Alright, and that, if we plug and chug those numbers, that is about 1,924 units produced. Okay. So then part C asks, which of the above options is a better choice for the company? So the budget constraint has not changed. This company is only able to spend $378,000 on its production elements no matter what. And if we spent it this way, as dictated in part A, then we are able to produce 1,406 units of whatever our product is. If we spend the money this way, as outlined in part B, we're able to produce 1,924 units. So it seems that the best choice for the company out of these two is going to be part B, right? Option B, where we spend $200,000 on X and $178,000 on Y, whatever those may be. Right? So for part C, so option B is the better choice for the company. Okay, so that answers the immediate question of which one is the better choice. But we're not just trying to figure out, here's two options, which one is better. We want to figure out how to make the best choice. Okay, so we need to figure out how to make the best choice. Okay. Which means we need to figure out how to maximize production subject to the constraint. Okay, so not only which option is better, right, but we don't know that 1,924 units being produced is the best way for them to maximize their production. There could be other amounts of production that actually are greater than that. Okay? But we won't know that unless we can actually maximize this value subject to our constraint. Okay, so let me just show you kind of what this looks like on a graph, so on a contour diagram. So here we are on Desmos. So notice up here I have my function. Okay, so this is our production function, and those give us a few contours. So I have a contour here at 1,000, at 2,000, and at 3,000. Okay, so those are the production values, right? So in other words, if you're on this contour of 1,000, that's the first one here. That's, if I can get it. So that's this contour, this first one. If you're on that contour, that means that you are currently producing 1,000 units of whatever your product is. Okay? If you are on the 2,000 contour, the second one, then you're going to be producing 2,000 units, and etc., and the 3,000. Okay, if you keep going. Now, if money was no object, they could just keep producing more and more and more, and this would just go on forever. But here's the constraint. So this is the constraint function. Notice it's linear. If I graph that and see what it does to the function here. So notice anything that lies on this line fits within that constraint, okay? Because we're utilizing all of our money. So you could go below the line, but there's really no point in going below the line, because then you're just like saying, oh, I have a budget of $378,000 and I'm not going to spend all of it, right? I'm only going to spend a certain amount. But the company wants to produce as much as possible, right? Because that's what makes them the money. So anywhere on the line is going to be subject to the constraint, okay, as we go all the way up and down it. And notice that as we move, we hit a couple of these contours. So when we're here along this contour, that's the 1,000 contour. So that's about how many units, okay, the value of x and y that it takes to produce 1,000 units. Okay, and as we start moving in towards the center here, right? What did we have for we had 1,000 units of x and about 2780. There it is. So 1,000 units of x and 2780 units of y. That's right there. Okay, and then in our second part of the example, we had 2,000 units of x and 1,780 units of y right there. So notice this value is higher than this one when it comes to the contours. So this contour, the second one here, that one has a higher value. That's 2,000. Compared to the other one is 1,000. So the closer we get to the 2,000 contour, the higher production we're going to have. But notice once we get to a certain point in here, then we start going away from the 2,000 contour back to the 1,000. So that means that the further away I move from this point in here somewhere, I'm going to be getting smaller outputs and smaller outputs in both those directions. So somewhere in here is where our maximum is going to occur. Okay. Now the question for us is, how do we actually find that? Okay. So the way we can do that is by using what we call the method of Lagrange multipliers. So Lagrange multipliers are going to be used to maximize or minimize a function, so optimize f of xy subject to a constraint. So in order to do that, we need to solve this system of equations. So we have fx equals lambda times gx. So this value right there, that's a Greek letter lambda. Okay, so it's written kind of like that. Okay, so it's a Greek letter lambda. It's just a constant. So I should say it is variable, but we're just treating it like a number in this context. So we have fx equals lambda times gx, fy equals lambda times gy, and g of xy equals c. So we're going to have an equation that sets equal the partials with respect to x times lambda, partials with respect to y times lambda, and then this last one is the constraint. Okay, right, that's g of xy equals c. And the constraint is always evident because it's equal to a constant c. So we have three unknowns. Okay, so we have x, we have y, and we have lambda. And lambda is called the Lagrange multiplier. Right, named after the mathematician Lagrange. So if f has a constrained global maximum and minimum, then it occurs at one of the solutions to this system or at an endpoint of the constraint. Okay, so if f has a constrained global maximum or minimum, then it occurs at one of the solutions to this system or at an endpoint of the constraint. So those are the possibilities. So if we solve this system of equations, okay, and get the corresponding x and y values, that's going to tell us where the max or min occurs. And then it could occur there at an endpoint, and we'll see that in a little bit too. So lambda itself, this lambda, you'll see as we go through these examples, we're not always going to need lambda, but sometimes we will. Each one of these problems, it relies on your creativity a little bit to be able to solve these, because no two of them are necessarily solved the same way. Okay, so you've got to just trial and error, solve the system however you need to in order to get the solution. Okay, so let's go back to that example we were working before. Maximize f of xy equals x to the 2/3 times y to the 1/3, subject to our constraint, and x and y both being positive, okay, because you can't provide negatives of a product. Okay, so let's get all the partial derivatives that we need. So I'm going to need fx, fy, gx, and gy. Okay, so let's just do that right here. Okay, so fx, that's going to be partial derivative of this with respect to x, so that's a constant. So just leave that alone, and then apply the power rule to this. So bring down the 2/3 and subtract 1 from that power. So this is going to give us 2/3 x to the negative 1/3 times y to the 1/3. Okay, do something similar for fy. So fy, but this time, of course, y being the variable and x being a constant. So that's going to give us 1/3 x to the 2/3 y to the negative 2/3. Okay. And then gx and gy, well, the function g is just the constraint function. So that's just going to be this part right here, right? Because this is, right, g of xy equals c, a constant. So derivative with respect to x is 100. Derivative with respect to y is, in this case, also 100. So there we have our partial derivatives. So let's go ahead and set up our system of 3 equations. So remember, we have fx equals lambda gx, we have fy equals lambda gy, and we have g of xy equals c, right? Just whatever the constraint is. So those are the 3 that we're working with here. So let's go ahead and just set those up because we have fx, fy, gx, gy, and the constraint. So this is going to be 2/3 x to the negative 1/3 y to the 1/3 equals lambda times 100. We have 1/3 x to the 2/3 y to the negative 2/3 equals lambda times 100. And 100x plus 100y equals 378,000. So that's our system of 3 equations. And now we need to solve these for x, y, and possibly lambda. So in this case, if you notice, those first two have a nice relationship to each other in that this is equal to 100 lambda and this is equal to 100 lambda, which means in this particular case we can actually cut out the middleman and get rid of lambda altogether and just solve directly for x and y's relationship. So let's go ahead and do that. So let me just call that 1 and 2, using equations 1 and 2. Okay, we're going to get them equal to each other. So this will be 2/3 x to the negative 1/3 y to the 1/3 equals 1/3 x to the 2/3 y to the negative 2/3. Now this already looks kind of daunting to solve, but just treat these using the laws of exponents. So a negative power goes to the bottom of a fraction. So really we can just set these up as 2 fractions. So this is going to be 2y to the 1/3 over 3x to the 1/3. My thing doesn't want to work on me. what's going on here? There we go. And then that equals x to the 2/3 over 3y to the 2/3. We can then cross multiply. So we're going to get, when I multiply this one up here, on the left-hand side, we're going to get 6y to the 3/3, so that's just 6y to the first, equals 3x also to the first. Okay, common factor of 3, get rid of that, so we get 2y equals x. So once we have 2y equals x, so this is the relationship that we can now use, and now we're going to substitute that into the constraint. Okay, so substitute x equals 2y into the constraint. So that's going to give us, that's 100x, but instead of x I'll use 2y, plus 100y equals 378,000. So that's 200y plus 100y, so that's 300y equals 378,000. So we get y equals 1,260. And remember, x is equal to 2y, so that gives us x equals 2 times 1260, which is 2520. Alright, so we got our y value, we got our x value. So this is a point of potential optimization. So now, once we have the x and the y, it's asking us to find that maximum production. So we're going to go ahead and plug those in. So let me just separate this off here. So f of 2520, comma 1260. Right, that equals 2520 to the 2/3 times 1260 to the 1/3, which is approximately 2000.1. Okay, so we would get a maximum production of about 2000, right? 2000.1 using this x value and that y value. Like it mentioned up above here, the maximum or minimum could occur at an endpoint of the constraint, so we just have to be careful with those. So, but for the endpoint of the constraint in this case, right, we have 100x plus 100y equals 378,000. The endpoints are where x and y are at their extremes. Okay, so that would be where x is 0 and y is 30,780, or when y is 0 and x is 3,780. But in both of those cases, our function is going to turn into a 0 because either x or y would be 0. So we won't have to worry about those in this case, but I do want to state that just so we have it written down. So at the endpoints, f of 3,780, comma 0 equals f of 0, 3,780. Those are both 0. So production is not maximized here. Okay, so we can't have maximum production at the endpoints. Therefore, this has to be the maximum production value. Okay, because it certainly can't be at the endpoints. So, thus, the maximum value of about 2,000 occurs at x equals 2520 and y equals 1,260. Right, so that is our maximum value and our maximum production level in this scenario. So if we go back and look at the graph, and we see where we hit that contour of 2,000. So again, we expected it to be around 2,000 because that's where that contour is. And if I go right into the middle there, you can see there's 2520, 1260 is right there. So you can see that looks like it's right about spot on, okay, with what we actually found algebraically. Okay, using our methods. Right. Now, notice we did cut out lambda in this last example, so let's talk a little bit about lambda. So the value of lambda represents the rate of change of the optimum value of f as the constraint increases. Okay, so in other words, right, as my budget goes up, right, how quickly does my maximum production change, for example, right? So we didn't have to find lambda in this previous example, but let's go ahead and find it now and then interpret what it tells us. So we know that x, the maximum production occurs when x is 2520 and y is 1260. Y is 1260. So solving using either of the equations, it doesn't matter because they're both equal to 100 lambda, gives us lambda is approximately equal to 0.0053. Okay, so what this tells us is increasing the budget. So the budget, which again we'll just call the constraint in general. So increasing that by $1 increases production by 0.0053 units. So increasing the budget by $1 increases production by 0.0053 units, which seems really small, but clearly this business is working on a fairly large scale, right? Since they're working in the context of $378,000, and we're just adding $1. So, but multiply, if they did it by $1,000, then they would be getting about 5 units more production, right, than they have now. So it just depends on the context of the problem. So let's look at one more example. So if x and y are the amounts of raw materials used, the quantity Q of a product manufactured is Q equals x times y. Assume that x costs $20 per unit, y costs $10 per unit, and the production budget is $10,000. How many units of x and y should be purchased in order to maximize production, and how many units are produced at that point? And then we'll find and interpret the value of lambda afterwards. Okay, so we are at part A. So first up, we need to get the partial derivatives to be able to set up our system of equations here. So, right, we have fx equals lambda gx and fy equals lambda gy. We can go ahead, I'm just going to use q. So partial of q with respect to x, that's just going to be y, right? Because it's x times y, but if y is the constant, derivative of x is 1 times what's left over is the y. And then partial with respect to y is just x for the same reason. And then gx, so our constraint, our budget constraint is $10,000. So that means that our g of xy, our budget function, that's $20 for x plus $10 per unit of y, and they have $10,000 to spend on that. So gx is 20, gy is 10. Okay, so then we can set up the system of equations now. So that's right, fx equals lambda gx, fy equals lambda gy. So we have y equals 20 lambda. We have x equals 10 lambda. And we have 20x plus 10y equals 10,000. Okay. Now, the way we go about solving this, again, it changes from problem to problem, but what I'm noticing here is that I have y written in terms of lambda, I have x written in terms of lambda, and in this function, I have x and y. So what I could do is take these two values, plug them into the third equation, solve that for lambda, and then plug that back in to get x and y. Okay, that's what I'm thinking. So, let's go ahead and do that. So, substituting the first two equations into the constraint. So this is going to give us 20 times x, which is 10 lambda. Oops. Let me leave the lambda out for just a second. I'll put it in. So 20 times 10 lambda plus 10 times y, and y is 20 lambda, equals 10,000. There we go. Okay, so subbing that into the constraint here. Solving that for lambda, that's 200 lambda plus 200 lambda, so that's 400 lambda equals 10,000. Solve for lambda. Lambda is 25. And now, once we have lambda, we can go ahead and get both x and y, because they were written in terms of lambda. So, substituting gives the following. We have x equals 10 times lambda, so 10 times 25, which of course is 250, and y, which is 20 times lambda, so 20 times 25 is 500. So now we have our x and y values, 250 and 500. We need to also consider the endpoints. So the endpoints of the constraint are where x and y are at their largest or smallest. So in this case, that's going to be 500 and 0. Right? So our constraint, those are the values of x and y. So if x is 500 and y is 0, then we have 1,000 or 10,000. Or if x is 0 and y is 1,000, then we get 10,000. So our endpoints of the constraint are going to be 500, 0, and 0, 1,000. Again, these are endpoints because for x can go as high as 500 and still fit within this constraint, this one up here. And y can be as large as 1,000 and still fit within the constraint here. So that's why those are the endpoints. Okay. Get rid of that. What's going on here? There we go. Sorry. Some technical difficulties here. I don't really know what's going on. Okay. Anyway, so the endpoints of the constraint are 500, 0, and 0, 1,000. So when we look at the function evaluated there, we see that, in fact, both times it's going to give us 0 and q of 0, 1,000, because we're just multiplying x times y in the original function q. So thus, the maximum production doesn't occur here. So our maximum production has to occur at the x and y values that we found. Okay, so therefore, the maximum production is q of 250, 500, which if you plug those in, it's just 250 times 500. That is 125,000 units. Okay, so our maximum production is 125,000 units, and that occurs when getting 250 units of x and 500 units of y. So then for part B, it's asking us about the lambda value. So for part B, so we're going to have, we already know what lambda is. All right, we found that earlier. Lambda is 25. So since lambda equals 25, so since lambda is 25, if the budget increased by $1, production would go up by 25 units. Okay, so remember what lambda tells us. It tells us that rate of change of that optimum value. So if we're currently at our maximum production level, right, where we're making 125,000 units by spending $10,000, well, if I just add one more dollar to my production, then I'm able to produce 25 additional units going at this current rate. So we can use that to kind of make projections about how much money could we make, right? How effective could our production be if we go beyond this? So that brings us to the end of section 8.6, the end of chapter 8, and the end of all new material for the course. So great job, everybody, getting to this point. I know it's been a challenge to get here, a lot of really rigorous material, but you did it. You made it to the end. So when we come back next week, we're going to be looking at some review and heading up to that final exam. So we're almost done. Let's finish strong, and I will talk with you all next time.